Okay, welcome back to CSE 373. Today we are going to continue our exciting journey into the world of graphs. So as a reminder, on Monday we introduced this terminology of what is a graph, what is it used for, and we introduced a lot of terminology about them that we're going to kind of use in the rest of our discussion about graphs. And today and on Friday, I want to focus more on algorithms that process graphs that we use on top of a graph. In this first video for today, I'm going to mostly focus on reviewing some of the terminologies and concepts that we talked about on Monday, because it's really important that we have this solid foundation when we go on to talk about applications and algorithms for the rest of the day and kind of the rest of the week. So in terms of the learning objectives for today, in this lecture, I want you to be able to review not review, that's part of it, that was supposed to be in parentheses. We want to be able to compare various graph implementations like the adjacency list and adjacency matrix, and be able to choose appropriately from a specific, which implementation you want to use for a specific graph. We're going to be able to implement this idea of BFS and DFS and be able to synthesize solutions to graph problems by using one of those algorithms as a starting point. We're going to be able to describe this ST connectivity problem and write code to solve it and explain why we have to use the solution that we do. And we want you to be able to describe the shortest paths problem, write some code to solve it, and explain how we can use the shortest path tree that we'll talk about later to come up with a result. So in this first video, I'm mostly going to focus on review, but we'll talk about more applications and more of these problems later on. So the first thing I'm going to throw up here is a lot of text. Do not worry. I'm not going to cover all of these right now because all of this is the terms that we introduced on Monday's class. So I just wanted to put a kind of condensed version of all of the terms on Monday in one slide for you to reference later, but I'm not going to go through and talk about all these things. What I do want to talk about is quickly remind you, a graph is kind of this social network structure where we have nodes, which we also call vertices, and edges, these links. And like the formal definition of a graph says that it's a set of vertices and a set of edges, where an edge is a pair of nodes or a pair of vertices that says there's a connection between these two. And we talked about that one of the biggest differentiators and types of graphs is this idea of a directed versus an undirected graph. So here in this slide, I have a picture of a directed graph where the edges here have a sense of direction coming from an origin to a destination. The way we usually think about that is that edge, which is defined as a pair of nodes, we think about the ordering within that pair being important. Usually we'd say the first one is the origin and the second one's the destination. The other type of graph, though, is an undirected graph, one that has no sense of direction between two nodes. In that case, you don't draw these arrows, you just draw lines between them. Now, one kind of set of terms that probably got a bit confusing was when we were talking about neighbors and degree. And I want to spend a second talking about this. So when we're talking about neighbors or adjacent nodes, we're talking about nodes that from one node, there's an edge to another node. So any node that's next to the node that we're talking about. Now, one of the things that can sometimes throw us off is if we're thinking about a directed graph, do you only count the edges coming out of you to those other nodes, or do you also count the edges coming into you from other nodes? So we usually think about this differentiation between your in neighbors and your out neighbors in directed graphs only. So if you have a directed graph, you could think about the in neighbors as being the set of nodes that have an edge coming to you, and your out neighbors being the set of nodes that you have an edge to. Similarly, you can talk about the degree of those sets. So the in degree is the number of nodes that have an edge coming towards you, and the out degree is being the number of nodes that have an edge coming away from you. So coming from you to those nodes. So we usually will use those terms kind of frequently when talking about directed graphs, but notice those terms make no sense in the case of an undirected graph. There's no differentiation between in and out for an undirected graph. So we normally just think about neighbors and degree as being a more encompassing term for undirected graphs. That's all I really want to talk about on this slide. We will talk about these kind of terms quite frequently, so it's okay if you want to go back and review these. We'll use these terms a lot. So now I want to talk a little bit about what did we actually implement this graph structure as. So we had this idea of these like relationships. How do we actually write it up in some data structure? We showed a couple ways. So the first one was this idea of an adjacency matrix. So in the adjacency matrix, we had kind of a 2D array, or another way of saying that is an array of arrays, where we kind of stored information in both rows and columns. So we usually would think about for a directed graph as saying the rows represent the origins of an edge, and the destination represents kind of, the columns represent the destination where an edge might go to. And the adjacency matrix uses a lot of space to make an entry for every possible edge that could be in our graph. So from every node to every other node. And then we store a 1 in this entry if there's actually an edge in this particular graph we're talking about. So for example, if you want to ask, is there an edge here between C and B? And in this case, it's a directed graph. So we have to ask, is there an edge from C to B? We start by looking in the row for C, because the row talks about the origin. And then we need to ask, well, is there an edge to B? We look in the B column and we see a 1 here. So we could say, yes, there is an edge. There could be a question of what do you actually want to store in there? If you're in this 2D array, if you have unlabeled edges, meaning you just are curious about the presence of an edge or the absence of the edge, you could store something like 0, 1, true, false, whichever's fine. But if you have edge labels, like you want to know that there's a label between C and B for this edge, you could probably just store that label there. So this works for both labeled and unlabeled cases. Whoops, I didn't mean to hide that. Okay, so we talked about these this adjacency matrix being really great for a lot of operations, like adding an edge, removing an edge, and checking if an edge exists. Because these are arrays, we get constant time access to any particular index. Even for 2D arrays, you can get this constant time access for 2 indices that you have to specify, the row and the column. But when it came to getting the neighbors of either in or out for a node, we had to loop over that whole the whole column or the whole row, in which case there might be n elements there. Remember, we use the letter n to describe the number of nodes, the number of vertices, and m as being the number of edges. So we might have to do this O of n operation in order to get the neighbors for something. And it uses a lot of space because it's going to have an entry for every possible edge that could be there. In the worst case, there's n squared edges. So we are going to have to use a lot of space, which then kind of motivated another type of structure, which we called the adjacency list, where in this structure, we kind of save space by only storing the edges that are present. So the adjacency list, we have some kind of entry for each node, and then the entry at that node is all of the nodes that it references. So for example, in this adjacency list, because there's an edge from A to B and from A to C, the entry for A is the list containing B and C. Usually you'd implement this with some kind of map for the keys of like what are the nodes you're talking about. So you have easy lookup to say, oh, what are the keys? What is the list of edges for the key C? You want that to be a fast operation. But we talked about then you get back this list of the nearby nodes, the neighbor nodes, which is why we call it an adjacency list. It returns a list of the adjacent elements. And then you could do any operation by scanning through that list. So removing an edge would be something like scanning through that list, but getting the neighbors could just return that list, which is pretty nice. Now, this structure is oriented in a very particular way. For directed graphs, it makes sense to store the origin as the lookup and then the destination as the value that you're going to be mapping to. You could also store it the other way, but the most common is this way. Now, one thing I want to quickly mention about this picture is in this kind of picture at the bottom right, the keys and the values, the origins and the list of destinations, notice that we're drawing an abstract picture. Like, you probably might use a hash map for this mapping from keys to the values, but I don't need to draw all of the extra internal buckets and extra space. Remember that the hash map is just, in some sense, an implementation detail. This is just describing, oh, I'll use a map ADT to map the nodes to a list of all of their destinations. And so drawing this out, I'm not usually going to always draw every single internal detail that might be there. Now, the last structure we introduced was this kind of in-between. Instead of storing a list for the values in the adjacency list, we thought about maybe storing another hash map or another hash set of some sort. In the Monday video, I called this kind of like an in-between solution because it kind of had behaviors of both the adjacency matrix and list, using extra space for efficiency, but also kind of being organized in this adjacency list like way. Just to be a little bit more consistent, I'm going to call this an adjacency list, but specify that it's like one that's using more hashing. So it's similar to the adjacency list I just described, but now the values are going to be hash maps, where you might hash the destination as key, and then something like the edge label, or if 1 or 0, true or false, if the edge is present, as the value. You don't necessarily need to think about these things as being maps. You can think about them being as hash sets. That's totally fine. In the case of you don't care about edge labels. But this idea being is like you're using extra hashing to speed up the checking if a node exists. And this was nice because it usually gives us constant time for those same operations that the adjacency matrix does, assuming we're in the in practice case. And it's saving us a lot of space. One thing I thought I should highlight when we're thinking about this adjacency list structure or adjacency matrix for undirected graphs, the story is the same. You just usually have to be a little bit more careful when you're updating these structures. So for the adjacency matrix, if you're adding an edge between D and E, you have to, let me put this out. So say we wanted to add a connection between E and D. Well, we would need to change both this entry from E to D to 1, and we would also have to change D to E to be 1. So you usually have to remember to update both. Similarly, in the adjacency list case, you'd have to add E being mapped to D and map D being mapped to E, going to E. So you usually have to update twice. You just double the amount of information you're storing, but it makes it simplest for most of your implementations. So these representations work great for undirected graphs as well. Now, we talked a little bit about this on Monday as well, which is there are some trade-offs here between when should you use an adjacency matrix versus when should you use an adjacency list. Adjacency matrices take more space, and they're not always faster. Sure, adding an edge, checking if an edge exists, those are faster, they're constant time. But some of those other ones, like get all the neighbors, that took O of n time, even if you had relatively few neighbors. So these structures, the adjacency matrix, works really great with something that we call a dense graph. A dense graph is one where there are lots and lots of edges, like close to the maximum number possible of n squared. And in that case, the running times will be pretty close. And then also, because they're implemented with arrays, they generally have a much better constant factors. And we won't really talk about this too much, but there is some interest in actually looking at the properties of this matrix itself. If you've taken a class like Math 308, linear algebra, you could do linear algebra analysis on these matrices, which is really, really cool. Not something we'll talk about, but can be useful. And then you might think about, if I'm using an adjacency list, should I use the linked list or the hash table? Well, usually people end up using the hash table because it tends to be faster, but do remember it still can possibly hit that worst case. And the linked list actually could be pretty nice because most of the algorithms we talk about today, what you really want is just easy access to all of the neighbors of a particular node, and you don't really need any of the fancy hashing stuff for something like that. You could just use an adjacency list. So in our course, we almost always will assume we're talking about this hashing implementation using an adjacency list with hash maps. And if we ever want something different, we could describe that. It's important to understand these differences, but we're always going to assume that we're not in this worst case. We're always going to have this O of 1 runtime because we want to focus on the graph things, not so much the hashing things. So what I want us to do is I want us to do a little practice problem. So instead of asking who's this Pokemon, we're going to ask who's that graph. So I'm going to set up a problem here where I want you to describe what graph properties you might want to use given a particular situation. When I was making this, I was hoping this is still relevant. Pokemon was really big when I was a kid. And so this was a thing that was in the TV show, but this is not actually about Pokemon, so don't worry about it. So the context that I want us to try. AI2, it's a company that's kind of down the street from UW that works on a lot of AI applications. They have this tool called Semantic Scholar that lets researchers search through a large archive of published papers. Suppose we wanted to organize authors and papers in a graph such that it's easy to figure out which authors have worked on papers with other authors. So for example, the kind of question you want to answer pretty easily is, who are all the authors that have co-authored with me or with some other person? So describe the graph structure you would want to use here. What are the vertices? What are the edges? Is it directed or is it undirected graph? What labels are you going to use on that graph? And with this implementation, will it be a simple graph? Okay. Take a second, think through that, and write out your response. Okay. So let's take a stab at what we think. So I'm going to have all my answers here on the side. Part of this is it usually depends on what you're using it for. So I try to be very specific in saying you really want to do something with this operation, but it really depends on your context. So what operations do you care about? What do you want it to be easiest? What can you represent? So for being able to figure out how two authors are related, to me, I would say that's a good argument to make the vertices the authors. And then the edges would be something like author A and author B have co-authored a paper together. Now, in this context, should we have a directed or undirected graph? I think in this case, it makes sense to make it undirected because co-authoring isn't necessarily like a ordered relationship, like in the sense that if I say me and Eileen have co-authored together, it's not really clear like who should be an origin, who should be a destination there. Vertex labels or edge labels. I think it makes sense to have vertex labels so that you can look back and figure out for this node, which author does it correspond to? And edge labels, I think in this context, for just being able to figure out who's related to who, I don't think they are particularly useful. Maybe you might want to make, you could maybe include the number of collaborations between author A and B, but I didn't really specify a need for that in this problem, so you don't need to represent that. And would this graph be simple? Well, it depends. We would have to decide in our implementation, do you want to count someone co-authoring with themselves? Because in some sense that's true, but also it's not. And we shouldn't have any parallel edges in this undirected graph. Like I'm not going to have a co-author count with one person with 5 and the other one with the same person with 3. We'd probably just represent this as one edge. So we probably won't have self loops or parallel edges. So we think we could probably make this simple, but it depends on your context. Notice, if I was interested in answering a different question, I would probably use a completely different representation. Like if I wanted to track citations between papers, then that makes sense to store nodes as papers and edges as being a citation between them. So it all depends on what question you're trying to answer and how you're going to answer it. And so hopefully this will give us context for what we're going to be talking about in our remaining videos, where we actually talk about algorithms that operate on these graphs.